Good day, everyone. Welcome to lecture number 28 of Theory of Computation. And in this lecture, or with this lecture, we will start the discussion about the Turing machines. So up to lecture number 27, we were discussing about the push down automata. Okay. And we said the languages that are recognized by a push down automata are the context free language. Okay. So we know that what are regular language. So let me go back to regular language. So we know that regular language, they mimic, or we can say they are the problems that can be solved by a finite automata, or we can say that are solved by a DFA or an NFA. Okay, so regular language correspond to problems that can be solved by DFA. So if we have a problem, okay, and that problem, so if we have some problem and that problem correspond to a regular language, then we know that those problems can be solved by a finite automata, or we can say DFA or an NFA. So these are the regular languages, or we can say the problems that correspond to the regular languages. Now we know that outside regular language, there are some other problems which are not solved by a DFA or an NFA. For example, this kind of problem, 0 raised power n, 1 raised power n. So this kind of language we will see. So the language, or we can say the context-free language. So these are the problems. So context-free language correspond to problems that can be solved by a push-down automata. And we know that context-free problems, they all context-free languages have one subtype, that is deterministic context-free languages. And deterministic context-free languages are solved by, or we can say they are recognized by, a deterministic push-down automata. So we can say that the problem is, let me rub this one here, 0 raised power n, 1 raised power n. Okay. So these problems, for example, the problem of this type, okay, WCW or WCWR. Okay, so these kinds of problems, these are deterministic context-free language, and we know that these problems are solved by a deterministic push-down automata. Now, on top of these deterministic push-down automata, we have the problems of this type, 0 raised power n, 1 raised power n. Or we can say we have the problems that correspond to context-free languages. And these are solved by a push-down. So up to this point, we know we have completed this up to this particular point. Now, there is a question that, is there any problem, or we can say, is there any language that is outside this domain, outside the domain of context-free language? So is there any language? Have we come across a language that cannot be solved by a context-free, or we can say that cannot be solved by a push-down automata? And we have come across one such problem. And what was that problem? So the problem is, for example, this kind of problem, 0 raised power n, 1 raised power n, 2 raised power n. So this kind of problem. Can we solve this kind of problem by a push down automata? No, we cannot solve this kind of problem by a push down automata. So that means, what does that mean? It means that there are some languages, or we can say some problems that cannot be solved by a push down automata. Okay, so there are some problems that are outside the domain of context free language. So this class of languages that we can say mimic, or we can say that will cover all the problems that are in the domain, in this domain, or we can say the problems. So this set includes the problems that can be solved by any computing machine. Okay, the set of all problems where there exists a computing machine to solve such problems. Okay, so this entire set contains all problems that can be solved by a computation machine, or we can say this set includes all languages that can be recognized by some computing machine. By some computing machine. And you can say that in this set, in this particular set, there are some problems that are solved by a DFA. There is another set of problems that are solved by a PDA, and these entire problems, or we can say the languages that can be recognized by some computing machine. This set includes all those languages, or we can say all those problems. Now, another question that we have to answer is there any problem outside this set? Is there any language outside this set? So what does that mean? It means that is there any problem that cannot be solved by a computing device, by any computing device. Okay, so let me rewrite it here. So let me make this again. So these are the regular languages, okay, and these are recognized by a DFA, or we can say NFA. Outside the domain of regular language, we have, so I am not writing all the languages, so only some. So we have context-free language, and these are recognized by a push-down automata. Okay, and outside this domain, we have, or we can say the domain that includes all those languages. Also, this particular includes all the languages such that there is some computing device for its recognition. So this red set includes regular languages as well as context-free languages, and also some languages that are not context-free languages. For example, this kind of language. Okay, or we can say this set includes all problems that can be solved by some computing device. Okay, so our question is, the question is that is there any problem outside this set? Is there any language outside this set? Or what does that mean? It means that we have to say, is there any language such that there is no, is there any language such that there is no computing device to recognize it? Okay, or we can say it also corresponds to, is there any problem such that there exists no computing device to solve it? Okay, so computing device, we can say, is there any problem such that there exists no algorithm to solve it? Okay, so we have to answer these questions. So first we have to answer this one. So what is the first question that we have to understand in this particular topic or in this particular discussion? The first thing that we will be discussing, the problems that are solvable. Okay, or we can say we have to discuss the set of languages that are recognizable. What is the meaning of recognizable? Recognizable here means that there exists some computing device to recognize this set. So this set of languages that are recognized, so all those languages, this set, so all those languages are called recursively enumerable languages. So this red set that we are discussing, so it includes all those languages that are recognizable, or we can say the language such that there exists as a computing device for those languages. So this set, these languages are called recursively enumerable languages. So if anyone says what is a recursively enumerable language? A language for which there exists a computing okay. And since context-free language is a subset of recursively enumerable language, so that means context-free languages are also recursively enumerable languages. Likewise, regular languages are context-free languages as well as recursively enumerable languages. Okay, so this is the first part that we have to discuss. The problems that are solvable, or we can say set of languages that are recognizable, or we have to discuss recursively enumerable languages. And the computing device for recursively enumerable languages is called a Turing machine. Okay. So that means for any recursively enumerable language, there exists a Turing machine. So here we know, for example, this kind of language, 0 raised power n, 1 raised power n. We know this language is a context-free language. Okay. So if it is a context-free language, so that means there exists a PDA. And we know context-free language is a subset of recursively enumerable language. So this language is also a recursively enumerable language. So if this language is a recursively enumerable language, so that means there exists a Turing machine for this language as well. So what I am saying, that 0 raised power n, 1 raised power n. So this is a language. So if somebody says, is there a PDA for this language? Yes. So answer is yes. So is there a DFA for this language? The answer is no. Why? The answer is no, because it is not a regular language. Okay. So is there a Turing machine for this language? The answer is yes. Because why there is a Turing machine? Because we said that Turing machine is a computing device that recognizes all recursively enumerable languages. And 0 raised power n, 1 raised power n is a recursively enumerable language. So that means we can design a Turing machine for this language as well. But we have to first understand what is a Turing machine. So we will first understand what is a Turing machine. Okay. And then we will see what kind of languages are recognized by Turing machine. And we know the languages that are recognized by a Turing machine are called a recursively enumerable language. So after completing this, we will then discuss, is there any non-recursively enumerable language? So we will discuss this. So what does that mean? We have to discuss that, is there any language such that there exists no computing device for that language? So if we are able to answer this question, we will also answer, is there any problem that cannot be solved? So we have to answer this question as well. So from this discussion, we have taken out 2 points. The first point is that all, or we can say recursively enumerable languages correspond to problems that are solvable. Or we can say recursively enumerable languages correspond to problems that can be solved by a Turing machine. Okay. Second point that we have taken from this discussion is that, so if there is a problem, or we can say if there is a Turing machine for a problem, this implies the problem is solvable, or we can say it implies there exists an algorithm. Algorithm means solution. Okay, so algorithm here means solution. There exists an algorithm to solve the problem. Okay, or we can say that the third point we can take, if there is a solution, or we can say there is an algorithm for a problem, this implies there exists a Turing machine for the problem. So Turing machine is a limit of computation. So Turing machine is a limit of computation. Okay, so it is a limit of computation. So what does that mean, limit of computation? So limit of computation means that we cannot solve a problem if there is no Turing machine for that problem. So from these 2 points, 2 and 3, we can say, we can write these two in a combination as that if there exists a Turing machine for a problem, it is equivalent, or I can write this implies it is equivalent that there exists an algorithm for the problem. And it is, we can say the opposite is, if there exists no Turing machine for a problem, it implies there exists no algorithm for the problem. So this particular statement is called Cherished-Turing thesis. So this was the thesis of Cherished and Turing. What is the Cherished-Turing thesis? The Cherished-Turing thesis is saying that if there exists a Turing machine for a problem, it implies there exists an algorithm for the problem. So we will discuss it in detail, but you have to keep this in mind. So our first point is to understand what is a Turing machine. Okay, so let's first understand what is a Turing machine. Then we will see the languages that are recognized by a Turing machine. And after that, we will understand the limits of a Turing machine, or we can say what are the problems that cannot be solved by a Turing machine. So let's start the discussion about a Turing machine. So what is a Turing machine? So let us start the discussion about a Turing machine. So let's see what is a Turing machine. So for example, in case of a PDA, push down automata, or we can say in case of a finite automata like DFA. So in push down automata, we have one finite control. Okay, so this was our control. Okay, or we can say finite control here means finite states. And in PDA, we have an input tape. So this was our input tape. Okay. So this was input tape. And we were having an stack memory. Okay. So this was our stack. And this finite control, it has two heads. One head was on this input tape and another head was pointing to the top of stack. Fine. Likewise, in case of a DFA, we were having a finite control. This was our control. We were having an input tape and there was a head that was on this input tape. This head was moving from left to right, and this head was moving from left to right. Okay, and this head, stack head, it was moving in both directions. Sometimes down, sometimes up, based on the operation, push pop operation. Fine. And also in both these scenarios, in PDA and DFA, we were saying in both these cases, we were saying that our head, the head attached to, or we can say tape head, it was moving from left to right. Okay. And our automata, this PDA or a deterministic finite automata, it stops when the input ends, or we can say when our tape head reached to the last symbol of input. Last symbol of input. Fine. And when it has reached to the last symbol of input, or we can say when the tape head stops the processing of input, at that point we were seeing whether this automata, PDA or DFA, okay, whether this PDA or DFA is in the final state or in a non-final state. Okay, so if it is in a final state, we are saying that it has accepted the input, and if it is in non-final state, we are saying it has rejected the input. Okay, so this was the scenario. Now in case of a Turing machine, so in Turing machine, we like these two, push down automata and deterministic finite automata, we have this finite control. This is our finite control. Okay. So finite control means that there are finite number of states. Okay. There are finite number of states. And we have this input tape. And this input tape, it is unbounded on both the directions. Unbounded on both directions. Okay, this direction as well as this direction. Fine. So this is our input tape. Okay, so let me write it. It is our input tape. Fine. And this finite control has a tape head attached to the input tape. So this is tape head. Tape head. Okay, so these are the components of a Turing machine. And this tape head here, tape head moves in both the directions. In both the directions. That means this tape head moves in the left as well as right. As well as right. In case of a PDA or a deterministic finite automata, this tape head was moving in only one direction, left to right. However, here tape head moves in both the directions, left as well as right. Moreover, there are some initial symbols on this input tape. So there are initially all locations contain blank symbol. Blank symbol. So all locations contain blank symbol. We can represent black symbol by this. Okay. Or we can represent it by dollar. So let's use this particular always, this one as a blank symbol. So initially all locations contains blank symbol. Now, if we have to check whether this machine accepts the input or rejects the input string is first placed in this on this input tape. So input string is placed on input tape. Okay. And tape head initially points to the start of input. Okay. So like in case of a PDA and DFA, the input tape or tape head first initially points to the start of input. Then what happens? So this tape head, so or we can say the finite control. Finite control. So what it does, it reads input symbol to which tape head points. Okay, so it reads something that is there on the input tape. Okay, then updates its state. Okay, and after that updating its state, what it is doing, there are two things it can do. One, that it is doing the first thing. So this is the processing. Then after the first processing, after this updating the state, what it is going to do, first thing that it is going to do, it will rewrite a new symbol at that position. Okay, fine. The second thing is that tape head moves. So it moves either in left direction or in right direction. So we can say that a transition of a Turing machine. What is a transition of a Turing machine? So can anyone say? So from above you can see how does a Turing machine makes a transition. So it has a state, it reads an input. Okay, so it is the current state, reads the input, and after reading an input, it updates its state. So new state is Q dash. So it moves to a new state. Fine. Rewrites a new symbol. So let's say it rewrites A dash. and then moves in the left direction or in right direction. Okay, so it moves in left direction or in right direction. So the transition in case of a Turing machine is like this: E dash and direction. So this direction can be left or right. If I am writing left, that means the tape head will move in the left direction. If I am writing R, that means the tape head moves in the right direction, but it will move after writing this new symbol. So you can see that in our Turing machine, so we have the following: we have states, okay, we have the input symbols, fine, we have the initial state Q0, fine, we have these symbols, or we can say the tape symbols that we rewrite, fine. And what else we have? We will see what else we have. We have another special symbol called a blank symbol. But you have to keep in mind this sigma will be subset of this one. Okay, so you have to keep this in mind. And this spatial symbol does not belong to this alphabet set. So it is yours. So you should think about this. Why this rewriting symbols should be subset of this input alphabet set. So you have to understand why this should be always true. Okay. And also we have a transition function. And transition function in case of a Turing machine is from a set of states and input to set of states, new symbols to be written, and direction. Direction can be left or right direction. So let me make you understand here. So we have a Turing machine. Fine. So this Turing machine has this as finite control. Fine. And this is the input tape. So let's say I have to say whether this Turing machine accepts this particular string. What kind of string? Let's say 1, 0, 1, 1. Okay. So I will initially have the head pointing to this. Fine. And this Turing machine, it will be initially in Q0 state. Right? Now it is reading 1. So Q0 on reading 1. I have to see what will be the transition on Q0 and 1. So let's say on Q0, it moves to Q1 if it sees 1. And then it rewrites a new symbol. Let's say it is rewriting a blank symbol. And then it will move in the right direction. Okay. So what will happen after this? So what will be a new state? So the new state will be Q1. And this head moves in the right direction. But before moving in the right direction, it has to rewrite blank symbol here. So it is rewriting blank symbol. Now it moves here, this position. Now let's say it is in Q1. And what is the input? The input is 0. So let's say it is saying if it is in Q1 and input is 0, it will move to, let's suppose, again Q1, and it will rewrite. It can rewrite anything. Let's say it is rewriting 1 and it is moving left. So that means now this, because of this transition, it will rewrite 1 here and then it will move to the left. That means now it is pointing to this blank symbol. Fine. So this is the input tape. And these are the transitions. So in Turing machine, we have Q. Q is the set of states. Fine. Okay, so let me rub some portion here. So we have set of states. Then after that, we have this Q0 is our initial state. Okay. Q0, then we have input alphabet, set. Also, we have the symbols to be rewritten. Okay, and we have this symbol, which is a special symbol called a blank symbol. Fine. And we have a transition function. This is a transition function. So transition function. So this transition function is from set of states and input alphabet to a state, tape alphabet, and the direction. The direction can be a left or right. So these are the 1, 2, 3, 4, 5, 6 things. Now what else remains? Now we have to see when will we say a Turing machine has accepted or rejected a string. So when will we say that Turing machine has accepted or rejected a string? Or we can say when we will say a Turing machine has completed the processing of a string. For example, in case of a PDA, or we can say in case of a DFA, deterministic finite automata, the tape head, so in case of a DFA or PDA, the tape head was moving only in direction, left to right, only in one direction. And when this tape head reaches to the last symbol, at that point, we were saying that PDA or DFA has stopped, or we can say has completed the processing of a string. And after completing the processing of a string, we were checking whether it is in final state or non-final state. However, this is not true in case of a Turing machine. Why? Because in Turing machine, the head moves in both the directions. So it may be possible that it will never reach to the end of the string. Or it may be possible that it is still computing after the end of a string. Or it is only going in the left direction. So there is a possibility. So when we will say that Turing machine has completed the processing of a string. So we on our own cannot say the Turing machine has completed the processing of a string. The Turing machine itself decides when to stop. So when it stops, it will go in two of the states. It will either go in one special state called accept state, or it will go in another spatial state called a reject state. Okay. So for example, in case of a PDA and DFA, there were only two types of states: final states and non-final states. However, in case of a Turing machine, there are states, so which are our normal states, and from those states, there is one spatial state called accept state and another spatial state called reject state. So apart from these states, there is an accept state and there is a reject state. So if Turing machine at any point during the processing of a string, so what I am saying, you have to keep this in mind. So if a Turing machine at any point during the processing of a string, during the processing of a string, goes into the accept state. Into the accept state. So if at any point, so it is not necessary that it has completed the processing of a string. So at any point during the processing of a string, Turing machine goes into the accept state. We will say Turing machine has halted. Halted means it has stopped and accepted the string. Accepted the input. Likewise, if a Turing machine at any point of time, so if a Turing machine at any point during the processing of a string, during the processing of a string, or we can say string here means input, goes into the reject state. So if it goes into the reject state, so that we will imply that Turing machine has halted and rejected the input. Rejected the input. Fine. Now, if it is in some other state during the processing of a string, so other states, there may be, for example, there may be multiple states. Okay. And there are two spatial states. One state is this, and another spatial state is this one. So this we will represent it by Q accept ACC, and this we will represent by Q reject. Fine. Now, if Turing machine goes into this state at any point, we will say it has halted and accepted the input. However, if it goes into this state, Q reject state, we will say Turing machine has halted and rejected the string, or we can say rejected the input. Rejected the input. And if Turing machine has stopped in any of these states, so which are neither accept state nor reject state, we will say that Turing machine has halted and we don't know. We don't know whether it accepts or rejects. Okay, we don't know about this, whether we won't say whether the input has been accepted or rejected. We cannot say anything about that particular input. And you will see that we will discuss this, that sometimes Turing machine goes into a loop, into a loop. That means it is not stopping working. It is continuously running, continuously running. So in this particular scenario also, we cannot say whether the string is accepted or rejected. I will explain this with the help of an example, but you have to keep this in mind. So it is possible that your Turing machine is designed in such a way that it will halt, or it is designed in such a way that it will go into a loop for some inputs. Okay, fine. So when we will say that a string has been accepted, so a Turing machine accepts a string if, so Turing machine accepts a string if it goes into an accept state, and after going into an accept state, it halts. Or we will say that it has rejected the string if it goes into the rejected state. Fine. So other thing that you have to keep in mind, that I make a small mistake here. So the mistake was this. So let me rub this here. So basically it should be other way around. So basically it should be that sigma is subset of okay. Fine. So this was all about a Turing machine. So we can say the brief discussion about a Turing machine. Fine. Now let's write a small example here. Okay. So let me write an example. Let's say we have to design a Turing machine for the following language. The language is L is equal to W belongs to A comma B star such that W ends with B. So we have to design a Turing machine for this particular language. Okay. So whenever you design a Turing machine, you have to keep in mind all the possible scenarios. Okay. So what are all the possible scenarios? So what I mean to say here, so this is our finite control. Okay. And this is our input tape. From this, we have the input tape here. This is our input tape. So the input is here. Fine. And this finite control first moves to the initial symbol of input. So let's suppose this is the initial symbol. Okay. And on left of this, we have a blank symbol. So here also we have blank symbol, because when there is no input on the tape, every symbol or every location contains the blank symbol. Okay. So this Turing machine starts from this position. So in this Turing machine, so you can see that we have to accept only those strings which end with B. Okay. So that means when I am processing this input, I don't care about these symbols. I have to only care about the last symbol. So what I am going to do, I will go to end of input. End of input. So how will I determine the end of input? So can anyone guess in this scenario how I will go to the end of input? I will keep on moving where? Right. So till what point? Till the point when I encounter a blank symbol. Blank symbol means that on left of this, there is the last symbol. So I have to first to go here to this blank symbol. So when I see this blank symbol, I will then go to the left, one position to the left. Okay. So how I will do it? I will go to the end of input. So end of input, how I will determine the end of input? When I encounter a blank symbol. Okay, blank symbol. So when I have encountered a blank symbol, then I will move one position left. Okay, one position left means that I will go to the last symbol. So that will be the last symbol of input. Symbol of, okay. So after going to the last symbol of input, if last symbol is B, if last symbol is B, then go to accept state. Go to accept state. Else go to reject state. So that means this Turing machine will accept only those inputs where the last symbol is B. Okay, and all other inputs, it will reject those inputs. So this is the general algorithm. Now using this algorithm, I will design a Turing machine. I will design a Turing machine means I will design it as graphical representation. Okay, so let's say initial state is Q0. In a state of Q0, we can name this state. So let's say this is our start, this is our home. Okay, so let me make the DFA, oh sorry, make the Turing machine. So this is our home. This is the start. Okay, or we can say this is a state which helps us to go to the end of the string. So from this home, we will go to the end of the string, end of the input, because the first case is this, I will go to the end of input. So how I will go to the end of input? So we can name it home or go to end. Go to end. Okay. So basically you can name it Q0 or anything. So just for the understanding, I am naming it home or go to end. So let's rewrite it. So let's write it as go to end. Go to end. So how we are going to the end? So we are in this state. So let's name it Q0. So Q0 is our go to end state. Go to end. So when we have Q0, so on Q0, if A comes, so whatever comes, I will move on to the right. So whatever is coming, I will remain in Q0. And what should I rewrite? Because you know that in a transition, so the transition function of a Turing machine is like this: Q dash, new symbol to be written, and direction. So here I am saying that if I am in Q0, I will remain in Q0 and I have to rewrite a new symbol. But I don't need to rewrite anything here. I will keep the same symbol. So that means I am rewriting the same symbol. A is there, so I am writing A. And then I am moving right. So right direction. Okay. Likewise, if B comes, I will again Q0, B, and move to the right. Okay. So if A comes, B comes, I have to move left. Sorry, I have to move right. Okay. Always I have to move right. However, if in this Q0 blank comes, blank means that I have reached to the last here. So it means I have reached to the blank symbol. So if blank comes, what I should do? Now I should go to a new state. So let's say in the new state is Q1. Okay, Q1, and I should go to the left side. And what should I write here? I should keep this as blank. So I should not write anything. I should keep it as blank, and I should move left. Okay, left means that I am on this last symbol. Okay, B symbol. Now on this Q1, if B is there, then I should go to the accept state, Q accept. And I should keep B as B. I should not change anything on this input. And I can move in the left direction or right direction. I have my choice. So Q accept means I have accepted. Wherever I am, wherever is my tape head, I don't care. So I am in Q accept state. That means I have accepted. However, if there is something else at the end, something else means that if there is A, because there are only two possibilities, A and B, then I should go to the Q reject. And I should keep A as it is, and I can move in any direction, left or right. Okay. So let me make it in clear terms here. So if I am in Q0, so this is our Q0. So on Q0, so this is the transition. If A comes, A is the input, then I should write A and I should move right in right direction. So this is how it is written. So A, then this. So this says I have seen this input symbol. This is saying symbol to be rewritten. Symbol to be rewritten. And this is saying direction of movement. Okay. So on this transition, we will write it like this. Likewise, if B is there, we will remain in Q0. We should rewrite B and move right. Now, if this is coming, this one means on Q0, I am seeing blank. Now I am, what is the input symbol? The input symbol is blank. Blank means that I have reached to the end. Okay. So I should rewrite blank and I should move one position left. Now I am in state Q1. Okay. So which state I am in? Q1. So let's say Q1 is the last check, last symbol. So let's name it like this. So this is check, last symbol. Okay. So that means in this particular check last symbol, this one, Q1 state. If B comes, that means the last symbol is B. So we will rewrite B and we can move in any direction. Whenever I am writing capital D, D means that you can move in the left direction or right direction. It won't make any change. Okay. Then if it is this, I will go to the Q accept. Okay. However, if the last symbol is A, I will rewrite A and I can move in any direction, but I will go to the Q reject. So this is our Turing machine. So this is the Turing machine. This is the Turing machine for this particular language. Okay. So I have helped you to understand one simple example of making a Turing machine for one particular language. Right? So before stopping this video, we will discuss deterministic Turing machine. So what is a deterministic Turing machine? We have already discussed about the determinism. Deterministic Turing machine says that for every combination of state and input symbol, there is only one transition possible. There is only one transition possible. Okay. So this is the first point. Second point is any missing transition itself means that it goes to reject state. So if there is some transition that is not available, that means it will go to a reject state. That will be a deterministic Turing machine. So this particular example that we wrote here, so this is a deterministic Turing machine, DT. Fine. And you have to keep this in mind, keep some points in mind. The first point is what we have understood up to this point. First is when a Turing machine enters an accepting state, it immediately stops running. It immediately stops running and accepts whatever the original input was. So this is the first point. We have already discussed it. Second point is when a Turing machine enters a reject state, again it immediately stops running and rejects whatever. So this part immediately stops running, it is here, and rejects whatever the original input was. Okay. So this was some basic introduction about the Turing machines. Okay. Now from our next lecture, that is lecture number 29, we will discuss some more examples related to Turing machines, and we will see how we can design Turing machines. Okay. So let me stop this particular video here. Let's meet in the next lecture. Till then, goodbye.